Hi, welcome back. So today we're going to be talking about the quantum Fourier transform. But before going into this, I'd like to give a little bit of context about what we've been talking about lately. So last lecture, we were talking about iterative phase estimation, which was a procedure for estimating the eigenvalues um, of an arbitrary matrix. And the way that we did this is we basically performed a sequence of circuits which looked very much like the Hadamard test that we discussed in the previous lecture. And by chaining these together, one at a time, measuring an ancilla register, we can cause the quantum state that we input to iteratively collapse to one of the eigenvectors of the unitary that we want to probe. And further, by taking a look at the statistics of the zeros and the ones that we end up getting from the measurements, we can actually infer the eigenvalues of this transformation. And so this equivalently, because all the eigenvalues are the form e to the I some phase, that's why this is called phase estimation, because effectively learning the eigenvalue is equivalent to learning the exponent of the eigenvalue. So that is what we did previously. But the question is there a different approach that we could do? Well, the trade-off that we did previously is that the approach that I showed you the other day, it is very efficient from the perspective of learning. It actually gets the optimal scaling that we can expect, and it uses a very small number of qubits. The downside is that it requires a lot more classical processing than we might like to do a very high accuracy estimate. And so the question is, are there ways that we can trade off the quantum resources, i.e. how many quantum bits we use to represent the problem, and the amount of classical preprocessing? And the answer is yes. And today, what I'm going to be doing is I'm going to be showing you the quantum Fourier transform, which gives a way of converting from phases to bit strings. And this ability to convert from phases to bits, it essentially gives us a way of directly doing phase estimation, where we can get the phases that are created by applying a controlled unitary on different branches of a transformation, or different branches of a quantum computation, and then forcing the quantum computer to output those phases not through some statistical inference method, but rather directly as a bit stream on inside in a qubit register on the quantum computer. So that's what we're going towards. But in order to do this, we need to spend some time first talking about the quantum Fourier transform, which is the central trick to implement this phase to bit interconversion that we need in order to make this a reality. So first thing I'm going to do is I'm going to begin by talking about what the Fourier transform is more broadly. And then after I've gone into some detail about the Fourier transform, I'll begin by proving some theorems. Yay! And then I'm such a dork. All right. Then after we've proven the theorems, then I'm going to show how to implement the quantum Fourier transform as a circuit, prove that it works, and from there, likely we're not going to have enough time to get quite into the applications of the quantum Fourier transform. But the next lecture, I'm hoping to go into that and discuss applications to both phase estimation and also how arithmetic can be performed by using the quantum Fourier transform. Okay, so let's talk about what the Fourier transform is. That is not the window that I wanted. Great. So the Fourier transform, basically, well, it is one of the most important mathematical transformations that we have. The idea basically is that the Fourier transform transforms between two domains. So if we've got some signal in time, so say some signal f of t, this will transform to a frequency distribution of a new function, let's call it capital F here, over the frequencies. As a particular example, let's imagine that what we wanted to do is we wanted to be able to figure out the frequency of a sine wave. going up and down over here. Let me just draw a little bit further for this over here. And let's say the period of this is t equals 2 pi over some angular frequency omega. And what we'd like to be able to do is we'd like to be able to estimate omega within obviously some error, but we'll get to that issue later. So one way that we can do this is just to take the sine wave, if we have access to that function, and perform a Fourier transform. So it turns out that the Fourier transform of sine omega t is equal to, I believe it's 1/2 delta omega prime, or sorry, this is a Dirac delta. Delta omega prime minus omega plus delta omega prime plus omega. Okay, so it extracts, well, plus or minus the frequency back out from the result. So that's why we use this all the time, for the fact that Fourier transform, oh, I should put a line there, because the Fourier transform is extremely good at finding periodicities in data. It's also got another bunch of nice features. The other nice features, and this gets used in quantum algorithms as well, is that the differentiation under the Fourier transform ends up getting mapped to ordinary multiplication. And so this is very, very nice for solving differential equations, because we can use the Fourier transform to be able to interconvert between a differential equation and an algebraic equation, just by switching to Fourier domain, which is a beautiful thing to do. Another aspect where this gets a lot of application in both image processing as well as recently neural networks is from the convolution theorem. And the convolution theorem is basically ends up saying the Fourier transform of a convolution is equal to the product of Fourier transforms. And a convolution is of two functions is something like the following. You know, let's imagine we've got integral of f of t g of something like this. And the convolution of these two functions ends up actually giving us the product of the two Fourier transforms. So that's the this has a lot of value in convolutional neural networks, where you're trying to apply a filter over an entire kind of a layer of a convolutional network cheaply. Rather than approximating this integral, what we have to do is we just have to multiply two Fourier transforms. So, okay, cool. That's awesome. But the question is, how do we do this on a quantum computer? Well, to do this on a quantum computer, we first have to take a look at the discrete Fourier transform. And so the discrete Fourier transform is given by the following definition. Let Fn maps complex numbers, complex n-dimensional vectors to complex n-dimensional vectors be the transformation such that Fn of j equals 1 over root n sum over k equals 0 to n minus 1 e to the 2 pi I k j over n. Okay, so this is how we define in Dirac notation what the discrete Fourier transform is. We could translate this back to matrix language, which is normally how people think about the discrete Fourier transform on ordinary computers. And note that here, unlike the continuous version that I was discussing previously, all of this is finite dimensional. We can view this as a finite dimensional approximation to the previous one, or we could see this as the analog of a Fourier transform on a finite dimensional system. Okay, and it has basically exactly the same properties that we end up seeing for the continuous Fourier transform. So, claim is that Fn is unitary. Okay, and this is something that's very important because if the Fourier transform is actually a unitary transformation, that means that that's something that in principle, because quantum computers are unitary, can implement any unitary transformation approximately, that means that this ought to be something that a quantum computer could do natively. And so let's go through and prove that this transformation over here, in fact, is a unitary transformation. So Fn is unitary if and only if Fn inverse is equal to Fn dagger. Okay, so thus what we end up having is that for all x and y, if it's unitary, then we require that x Fn dagger Fn y is equal to delta xy for all computational basis vectors. Okay, so that's the idea of that we want to be able to demonstrate. So let's start with the simplest example. Let's begin just by considering first case x equals y. Okay, so if we have x equals y, then the quantity that we need to compute is now x Fn dagger Fn x. Okay, cool. So by the definition that we have above here, we know that Fn acting on the state x is equal to 1 over square root n sum k equals 0 to n minus 1 e to the 2 pi I k x divided by n acting on the ket vector k. Okay, cool. And so therefore, x Fn dagger can just be found by taking the Hermitian transpose of all of this. Root n sum k equals 0 to n minus 1 e to the 2 pi I kx divided by n k Hermitian transpose. Wonderful. And that is equal to 1 over square root n sum from k equals 0 to n minus 1, e to the negative 2 pi I kx over n k. Just using the fact that the sum over aj for any matrix j is equal to the sum over j aj dagger. So I just used the distributive property of the complex of the adjoint operator in order to be able to build this. All right, great. So now let's go through and take the inner product between this over here. So if we have that, then x fn dagger fn x, just by multiplying these two things together, ends up giving us 1 over square root n, sum over k and k prime, e to the 2 pi I k prime minus k over n k prime. And because this is equal to the Kronecker delta function, k prime, that is equal to just 1 over sum of k e to the 2 pi I 0 over n. That is equal to n over n equals 1. Okay. So that's happy. But now what we need to do is we need to look at the other case. Let's look at case 2, where we have that x is not equal to y. Well, if we have that case, then we can go through very similar reasoning. We end up getting that our inner product between x fn dagger fn y is equal to 1 over n sum over k and k prime of e to the 2 pi I k, I think it should be a negative, x over n, e to the 2 pi I k y over n, and then we have the inner product of k and k prime, just like we had before. Oh, and this should be a k prime up here. Okay, so we know exactly, just like before, that this, of course, is equal to the Kronecker delta function of k prime. So we know in the sum that all terms are going to be 0 unless k is equal to k prime. Therefore, this is the sum 1 over n, sum over k, e to the 2 pi I, k, y minus x over n. Okay, cool. And now, because of the fact that we've assumed that y is not equal to x, y minus x is an integer, because these are computational basis vectors. Okay, so an integer not equal to 0. That's going to be key. So now, when we take a look at this, we can actually end up rewriting this sum. This sum is just 1 over n, sum over k, e to the 2 pi I, y minus x over n to the k. And this, you'll note, is a geometric series. And I'll just be extremely clear at this step that I'm summing from k equals, say, 0 to n minus 1. All right, so then when I perform that sum, what I end up getting is I end up getting that this is equal to 1 over n e to the 2 pi I n y minus x over n minus 1. And here I just looked up the definition of a partial sum for a geometric series and plugged in the formula. You can find that by searching Wikipedia or looking at Concrete Mathematics or your favorite textbook. And so this in the denominator turns out to be, just using the formula, it's y minus x over n minus 1. However, these two cancel, and this is an integer. And so what we end up getting is that this thing is proportional to e to the 2 pi I m minus 1. However, e to the 2 pi I m, that's always equal to 1. And the way you can see this is just using Euler's identity. This is cosine of 2 pi m plus I sine 2 pi m. If m is an integer, then sine of 2 pi is 0, and cosine of 2 pi is 1. Therefore, we end up having this result, which means that this is equal to 0. Therefore, we have that in the case where x is not equal to y, we have x fn dagger fn y is equal to 0. And this concludes our proof. We showed that in the case where where x is equal to y, we ended up getting 1. In the case where it's not equal to y, we get 0, which corresponds to what we needed to show. We need to show that it's delta xy. So we've therefore concluded that the matrix has to be unitary. So that is an indication that this is unitary. Now, let's take a look at some examples. Okay, so first thing, just to remind ourselves, the transformation fn acting on j is equal to 1 over square root n sum from k equals 0 to n minus 1 of e to the 2 pi I kj over n k. Okay, I've just rewritten the definition of what a Fourier, a discrete Fourier transform does to a basis state j that's input into it. Okay, well, let's look at this for the case where n equals 2. For the case where n equals 2, fn acting on 0 is equal to 1 over root 2, 0 plus 1. And for the case where we have 1, this is 1 over root 2, 0 over here, plus e to the pi I of, e to the pi I 1, which is equal to 1 over root 2, using Euler's identity, just like I did before, minus 1. Okay, so this ends up implying that fn as a matrix can be written as 1 over root 2, just using our standard rules for computing a matrix. This ends up taking a form of that. And thus, this is the Hadamard transform. So we can end up viewing the Fourier transform is a generalization of the Hadamard transform for higher dimensional states. And in the case specifically where we have a two-dimensional quantum state, we end up getting that, the Hadamard matrix is the Fourier transform. And so to give some idea about why this is useful, let's take a look at the simplest transformation that we can think of. So let's consider, the case of the operator z. Okay? Now, if we have the operator z, this is just, of course, 1 minus 1, 0, 0. And we've used the identity a ton in order to be able to interconvert between bit representation and this phase representation equals x. So basically, what we have over here is this function z can be thought of as a phase flip. And this over here is a bit flip. So the quantum Fourier transform in 2 dimensions, which is the Hadamard transform, really can be thought of transforming the information that's applied to the system by doing a phase flip on half of the quantum state and transforming that to a bit flip, which gives us a way of actually measuring when a 180-degree phase ends up occurring in some part of a process. So this gives you the first sort of hint about how a Hadamard transform, i.e. a quantum Fourier transform, can be used in order to be able to extract the phase from some protocol just by converting it into a bit flip, which we can notice. Okay, so that is how the quantum Fourier transform ends up working. However, it's important to note that while the Hadamard transform satisfies h squared is equal to identity, we do not have that the Fourier transform squared is equal to identity. Okay, so while the Fourier transform is unitary, it is also not Hermitian. All right, so it's just the Hadamard transform, which is the only special Fourier transform that happens to be equal to its own inverse. The Fourier transform in general, we really do have to pay attention to whether we're applying Fn or Fn dagger to switch between effectively the phase basis and the bit basis. All right, so that is the simplest possible example of a quantum Fourier transform. So in order to be, the next step is trying to figure out how to implement the quantum Fourier transform. In order to implement it, we've got to come up with a more convenient expression for building it. I mean, we could just simply use this over here, find a matrix representation, and then use the brute force tools that we discussed about 2 lectures ago in order to be able to implement this as a sequence of arbitrary gates. But the problem is that the Fourier transform actually has a lot of special structure to it that we can take advantage of. And these special structures allow us to do the compilation actually with exponentially fewer gates that would be required versus the full brute force approach. So if we did a brute force approach using the 2-level reflection trick that we saw previously, this would require order n squared gates. And we'll see that we can actually end up doing this with order log squared n gates, which is exponentially better than what we would do with the brute force version. And by the way, the classical Fourier transform, if we wanted to implement this on an ordinary computer, this ends up requiring order n log n gates using the fast Fourier transform. So that is basically what we end up getting. The quantum version, actually, we're going to see, requires exponentially fewer operations than the classical version. However, this sounds amazing. because given how many applications there are for the quantum Fourier transform, or sorry, for the Fourier transform in general, getting an exponential reduction in the cost of it seems like quantum computing should be useful for just about everything in signal processing as well as related fields. However, it's not quite exactly the same thing, because the discrete Fourier transform will end up outputting the entire vector when we do it on an ordinary computer. You'll get psi 1 all the way down to psi n, or let's be good computer scientists and start with 0. And so if we have this kind of a vector, we have all of those numbers popped out when we do this calculation. If we do the unitary transformation on a quantum computer using, say, this brute force method, we won't get this vector. We'll get a quantum state that ends up being proportional to psi naught all the way down to psi n minus 1. If we wanted to be able to learn all of those individual amplitudes, we would have to repeat this many, many times, and the actual process of learning those values actually would be less efficient than doing it on an ordinary computer to begin with. So we've got to be very careful about when looking for applications for this technique, because reading the output from this transformation, well, exponentially faster than its classical analog, ends up killing the performance advantages that we end up getting. But we'll see some advantages later, and one of the key areas where this is used frequently is in factoring algorithms. But the transformation that we're going to need to rewrite this in order to make the symmetries of the problem manifest is the following. Okay, so if we rewrite the discrete Hamiltonian transformation, we can end up seeing that Fn will map a sequence of bits, J1, all the way through to Jn. Oh, by the way, this treatment that I'm doing is more or less ripped wholesale out of Nielsen and Schwang. So if you'd like any clarification about any of these things, the chapter in the textbook is fantastic. Okay, this ends up mapping to 1 over, let's say, yeah, okay. So I'll call this little n over here, and 2 to the n there, because I'm using a binary expansion. And this turns out to be writable as the following tensor product. E to the 2 pi I, 0.jn1, 0 plus e to the 2 pi I, 0.jn minus 1, jn 1, all the way down to 0 plus e to the 2 pi I, 0.j1 all the way down to jn1. All right, and that is the transformation that we're going to want to do. Now, the reason why we want to be able to write this in this form is because of the fact that we can very clearly see that the Fourier transform actually can be rewritten as a tensor product of all of these individual terms. So all we need to do in order to be able to implement the quantum Fourier transform is figure out how to build these guys. Once we've figured out how to build these guys, then we chain them together in order to build the entire unitary. And it's this tensor product structure that we're exploiting in order to get our exponential advantage over what we would have with a brute force construction. But first, let me show that these two things are totally equivalent. But I guess before that, I have to go and explain a little bit of notation here, which is this decimal expansion of this. So here, what I mean is this is kind of like a binary decimal. So, let's take our favorite number, which might be, 3.14159. Okay, we can write in decimal, this is 3 plus 1/10 plus 4/100 plus so on and so forth. Okay, we want to do the exact same thing with phases, or sorry, binary numbers here. So 0.J1 all the way down to Jn in this particular case would be J1 over 2 plus J2 over 4, because we're working in base 2, not base 10, plus J3 over 8, so on and so forth, going down to Jn over 2 to the n. Okay, so that's what this notation is meaning here. It's meaning this binary decimal expansion up here. All right, so now let's show that this ends up working. So to begin with, we end up having that Fn, just by definition, maps J to 1 over 2 to the n, sum from k equals 0 to 2 to the n minus 1, e to the 2 pi I j k over 2 to the n. Okay, and this is just the definition using capital N is equal to 2 to the little n. So we've assumed a binary expansion here. All right, and so now what I'm going to do is, speaking of binary expansions, I'm going to begin by taking this integer over here and representing it in binary explicitly. So if we do this in binary explicitly, we can write this as 1 over root 2 to the n, sum from first bit of k1 over through to the nth bit of k of e to the 2 pi I j times sum from I equals 1 to n of ki times 2 to the minus I. k1 through to kn. And so what I'm doing over here is I'm using the fact that, just like with decimal, if I have 1 over 10, that is 0.1. 1 over 100 is equal to 0.01. Similarly, in this decimal notation, in this binary notation, we have 1 over 2 equals 0.1, 1 over 4 equals 0.01, so on and so forth. So I'm just taking, for any individual k that we end up getting at the top, that value of k and writing it as a binary series, just like we did here. Okay, so I've just done that, but now, rather than summing over all k, I've also broken up the sum over every possible bit value that we get. So rather than doing the sums all together, I've summed over each of the individual bits that represents the integer k. Okay, so nothing's really happened here. I've just expressed the k explicitly in binary and broken the sum over all k's into the sums over the individual bits. Okay, so that's just a little bit of sleight of hand. Now, let's simplify this even further. So we can break this up over here by noting that there's an implicit tensor product structure inside this, because we have that, the state 1, 1 is equal to 1 tensor 1 in Dirac notation. So we're going to explicitly break up this sum over here into a tensor product. And the tensor product is going to be of the form tensor product of I equals 1 to n. So this is corresponding to each of the bits, the n bits that we have in the binary expansion for k, of e to the 2 pi I j k sub l of 2 to the minus l over here. Yeah, okay, sorry, I changed this to L so we don't get confused with the i's. All right, cool. So now that we've got that expansion, we can use the fact that the tensor product, the sum of A sub j, B sub j, this is equal to just the sum of no, that isn't true at all. Sorry. After some manipulation of this term, what we end up getting is that we can rewrite this whole expression as 1 over root 2 tensor product L equals 1 to n, now summing over the two particular values that we end up getting in this. So we sum over KL equals 0 to 1 of, and I guess this is has to be K over here. And now we're just expressing this out as a explicit sum 2ij k sub l 2 to the negative l k sub l. Okay, where I'm using the fact that just the tensor product in this form of L equals 1 to n for a bunch of matrices A sub L is equal to A1 tensor A2 tensor tensor AN. Okay, so I mean when I use this notation, it's just like pi notation for a product, but instead we're distributing a tensor product over all of the terms. Okay, great. So we have this particular form over here. The next question is, well, what do we do with this? Well, note that if KL is 0, then this term actually is 1. And so we can end up expressing this as product from L equals 1 to n of 1 plus e to the 2 pi I j, and I'll explicitly put a 1 in, but it's obviously not needed, e to the minus l, or 2 to the minus l up there, and oh yeah, this should be a 0 here, and that should be a 1. And then by expanding this out over here, we explicitly end up getting this is equal to 0 plus e to the 2 pi I 0.jn all the way down, just literally by expanding all of these tensor products out. 1, 2, 0 plus e to the 2 pi I 0.j1 all the way down to jn 1 over, this should be an n up here, that should be an n there, and here, and the rest is good. Okay, over root 2 to the n. So that is how we end up expressing or exposing this tensor product structure in the discrete Fourier transform. And then we're going to employ this in our quantum circuit implementation. So, in order circuit implementation. Okay, so in order to do this, to show the circuit, the first thing that I'm going to want to do is introduce a new operation. This operation we're going to find to be RK, which is just 1, 0, 0, e to the 2 pi I divided by 2 to the k. All right. And we can see that this actually is equivalent up to a global phase to RZ, if we're just looking at a single qubit, of two pi over what? Over, yeah, just 2 to the k. Okay. So this is our operation that we're going to try to build, and we're going to use this in order to be able to build up these fractions over here. And the reason why we're going to do this is that, okay, let's say we have RK to the J1 times, now, you know what, let's make it R2 to the J1 times R3 to the J2. Okay, then this would be equal to 1, 0, 0, e to the 2 pi I over 2 squared J1 multiplied through by 1, 0, 0, e to the 2 pi I J2 over 2 cubed. Okay, when we multiply these together, the matrix multiplication just turns into scalar multiplication. And we end up getting e to the 2 pi I J1 over 2 to the 2 plus J2 over 2 to the 3. Okay, which in this case, for example, we can write as 1, 0, 0, e to the 2 pi I 0.0 J1 plus, J2. Using the binary decimal expansion over there. So that is how we're going to be doing it, by combining different controlled versions of the R gates. We're going to be implementing applying these phases over here. So what we need in order to be able to do this is we need to be able to build a controlled RK gate. Now this is one of the ways in which this notation is very nice. The circuit that I asked you to do on the homework was to build a controlled version of the RZ gate. Now, the RK operation is equivalent to RZ up to a global phase, but even though those two are equivalent when applied in an uncontrolled fashion, these two are not equivalent. Okay? The reason why is because of the fact that the RZ will apply a phase on 0, controlled on whether the top qubit is 0 or 1. The other case will not. So you can see by taking a look at the phases that both of these output in different circumstances that there will exist inequivalent sets of inputs. And you cannot just simply multiply the resultant state by a constant phase factor in order to reduce one to the other. So these two are not the same thing. And that's why we've specialized to this operation up here. Now, actually, we ended up in a previous lecture finding a controlled implementation for this. And I'll just remind you of what that implementation ends up looking like. It involves using Toffoli control swap gates and a single qubit rotation or two. Okay, and so this will have a 0 over here. Sorry, we are going to want to begin by doing a gate of RZ of 2 pi over 2 to the k. And then we're going to do RZ inverse through the same angle. Okay. And then, because we've partially done a swap between the two, we're going to have to unswap down over here. And my claim is that this circuit ends up implementing the RK circuit. So, our controlled RK circuit. So the proof of equivalence is as follows. Again, we're going to boil this down to a bunch of cases. And we're going to look at all the computational basis state inputs, because if this circuit has the right properties for every computational basis state input, C and A over here, then we know that the circuit is generic. Note we don't have to require all that it has the right form for all inputs down on this line, because we're assuming that every single time you apply it, it's always 0 down there. So if C equals 0, then trivially you can see that this controlled swap never happens, this controlled swap never happens, and then all we have is RZ and its inverse. Therefore, this circuit implements the identity as required. So in the case where C equals 0 on the top and A is anything you feel like, life is good. All right. Now, what about if A equals 0? Well, if A equals 0, then our state's going to be of the form C 0, 0. If, regardless of whether I apply a swap here or not, the state is exactly the same. So this is always going to be just C 0, 0. So in the event that this is 0, the swaps do nothing, and they can be taken out of contention. Therefore, the phases do nothing. So this, in this particular case, we can see that it implements the identity, because whether or not the A qubit ends up getting swapped and going down here, the qubit that comes up in its place is identical. So we end up functionally applying, getting the opposite phase back for this bottom input, and we end up just getting something like e to the negative 2 pi I over 2 to the k plus 1 times e to the plus 2 pi I over 2 to the k plus 1 from this and its inverse, and the two phases cancel. So this causes us to implement just the identity transformation. So the only interesting case that ends up coming up is, let's consider the case where C equals 1 equals A. Then, in that case, we end up having a state 1, 1, 0. Now this maps to, when we apply the RZ operation, it'll map to e to the I 2 pi over 2 to the k plus 1 from the first transformation. Okay, so this is doing the RZ. Now we'll do the swap. The C swap maps this to e to the I 2 pi over 2 to the k plus 1, 1, 0, 1. Okay, great. Now we do the final RZ operation. And this is RZ inverse acting on 0 now, because we've moved up there. And this yields e to the I 2 pi over 2 to the k plus 1 times e to the I 2 pi over 2 to the k plus 1. 1, 0, 1. Now, let's swap this back. And this will end up giving us e to the I, just by definition, of 2 pi over 2 to the k times 1, 1, 0. So therefore, this ends up giving us a controlled RK gate as required. Wonderful. So now we can end up doing a controlled RK gate, actually for any k, because we just have to change the rotation angle that we stick in that in order to do it. So using just Toffoli, C0, and RZ, we can do this. Again, recalling that a controlled swap gate over here can be implemented as a Toffoli gate sandwiched between two C0 gates. Okay, wonderful. So that is how we do a controlled RK gate. So the next step is to ask, okay, well, how do we end up building the quantum Fourier transform circuit in general? Okay, so the way we build it is the following. This is the construction. We build it up by constructing each of the individual tensor products that are in the previous formula I showed you for the sum. So let's actually just go to that. So recall that when we go up to the kind of like optimized representation of the quantum Fourier transform, there's this tensor product between each of these terms. So what we're trying to do is we're trying to build each of them. Note that each of them is always exactly of the form 0 plus 1 divided by square root 2 n times. So we begin doing this by getting the 0 plus 1 by applying a Hadamard transform. Then we apply a controlled R2 gate going up, so on and so forth, going down to Jn minus 1 and Jn down at the bottom. Then we go through here and implement a Rn minus 1 gate, and finally a Rn gate up here. And again, the point is just to get the correct sequence of phases that we need for each of those tensor product terms up there. So now we've done one term, we'll go on to the next one. This one will be implemented by doing the exact same pattern that we did up here. We'll have an R2 gate, and I guess maybe I should have done a J3 in between, but you get the idea. It's controlled by that guy over there, so on and so forth, going all the way up to Rn minus 2 down here, and then Rn minus 1 down here, and so on and so forth, all the way through to the end when we do the last two, which are done just by the following here and H there. Now, the eagle-eyed amongst you might notice that there's actually a problem with this circuit, because the circuit, it outputs, let's zoom out a little bit because I didn't give myself enough space. It will output 0 plus e to the 2 pi I 0.j1 going all the way down to jn 1 over here. And this one all the way down will be giving us 0 plus e to the 2 pi I 0.jn acting on 1. So the interesting thing is that this implementation of the quantum Fourier transform circuit, it sort of does the right thing, but actually it reverses the order of the bits in between. We wanted this one to be the lowest order bit, and we wanted this one to be the highest order. So if that's the case, then in order for us to be able to do this, we need to actually kind of amend the result either logically or physically by carrying out swaps down here. And by logically, I mean that we'd have to keep track of whether or not the basis has been swapped here and adjust the rest of our circuits to use the opposite bit encoding. Technically, this is what this, for those of you who are used to this terminology, what this will do is if we envision all of these as a binary encoding of an unsigned integer, what it does is it causes big endian to go to little endian. If you don't know that jargon, don't worry about it. It's not super important, but I just wanted to mention it for those people who do, because it creates this kind of formatting difference when you output these. And so this actually turned out to be kind of an important issue. I remember my early days at Microsoft, one of the members of our team, he was writing a quantum programming language, and he was struggling because of the fact that he couldn't get Shor's algorithm to be able to actually output the correct factors with high probability when he was simulating a example of quantum factoring. And so the reason why this ended up failing was because of the fact that the paper that he was implementing forgot that the order of the qubits is flipped at the end of this and didn't include the sequence of swaps. So when he directly applied the factoring circuits that were in the papers, this failure ended up occurring. So I mention this because of the fact that it's quite possible for people who really know their stuff to ignore this subtle fact that if you use this construction for the quantum Fourier transform, that all of your bits are going to be in reverse order. And you either have to explicitly swap them, like I've drawn over here, or implicitly swap them by just making sure the rest of your circuit interprets the bits in reverse order. Okay, cool. So that is that. Now, of course, we come down to the final bit, which is proof that the circuit works. Okay, so first, let's begin with the bottom. So if we have H acting on Jn, what does this end up yielding? This ends up yielding, well, of course, we've all done Hadamard transform to death. It's just 1 over root 2, 0 plus 1, and 1 over root 2, 0 minus 1. Okay? And if Jn equals 0 otherwise. Okay, so that is what we end up doing. Now we can write this actually in a kind of a sneaky way. We can say, actually, this is equal to 1 over square root 2, 0 plus negative 1 to the Jn 1. Okay, because if Jn equals 1, we get the minus sign, so we can just write it like that. Okay, cool. So now, let's use a fact that negative 1 equals e to the I pi. And we can do this just by using Euler's identity and seeing this is cosine pi plus I sine pi, which is, of course, equal to -1. So when we do this, we end up getting that this can be written as 1 over square root 2, 0, plus e to the I jn pi 1. And now I'm going to do something really kind of lame looking. I'm going to just divide this through by 2 and multiply by 2. And this I'm going to therefore write as 0 plus e to the I 2 pi 0.jn using our binary decimal notation. So we can see that since the transformation that we wanted ends up applying something. Okay, where's the right form for this? Yep. Applying this factor, we see that we get it just by the Hadamard transform. All right, cool. So now that we get that coming out of it, let's actually go forward and then take a look at the next case. Let's say we have Jn minus 1, Jn, Hadamard, R2, controlled, there. All right, now, first thing, we see that the Hadamard transform, just as we argued before, ends up mapping Jn minus 1 and Jn maps to 1 over root 2, 0, plus e to the I 2 pi 0 point Jn minus 1, 1 Jn. Okay, now what we do is we do the controlled R2 rotation. And the controlled R2 rotation, where recall R2 is just 1, 0, 0, e to the I 2 pi over 2 to the 2. So this process can be actually viewed as only adding a phase conditioned on the value of Jn. And so this conditional phase can actually just be simplified as 2 pi 0.Jn minus 1 Jn, because 2 to the 2 is 2 decimal places shifted over on this side. All right, so we see that in this case, everything works. It's actually straightforward to see that inductively, we have that if we have Jn minus m over here, Hadamard, and then R2 on the next line below, and R3 on 2 lines below, so on and so forth, going through to R to the m plus 1, we end up getting that, where this is acting on Jn minus m plus 1, Jn minus m plus 2, all the way down to Jn. Okay, it's very easy to see that the state that we end up getting out in the end is 1 over root 2, 0, plus e to the I 2 pi 0.Jn minus m, so on and so forth, going all the way up to Jn 1. And then, of course, obviously, tensor producted with all the ones that we haven't had Hadamard transformed, going all the way down to Jn. So that is the proof that this ends up working, because of the fact that in general, this does the correct transformation needed to recapture each of these individual transformations after flipping the bit order appropriately. Cool. So the only thing left is to ask, okay, well, what is the circuit complexity for doing this? Well, we can see that this operation over here requires order M gates. Now, each RK requires order 1, or I should say controlled RK, requires order 1 operations from the gate set H, R, Z, C naught, as we can see just from this construction here. So because this only requires order 1 operations from there, the circuit complexity needed in order to implement one of these from this gate library is also order M. Now we have to do this for each M from 0 going to n minus 1. So if we have to do that, then our sum is going to be of the form sum over the cost of each of them from m equals 0 to n minus 1. And this, because this is order m, we end up getting that this is element of order sum from m equals 0 to n minus 1 of m, and that is equal to order m squared, or sorry, n squared. So the gate complexity of doing this using all of these rotations ends up scaling quadratically with the number of bits. In contrast, the fast Fourier transform, which is one of the best methods known for doing the Fourier transform, requires order 2 to the n times n arithmetic operations. So even if we equate an arithmetic operation to a fundamental gate operation that we end up having on this side, the FFT requires exponentially more of these more complex operations than the quantum computer requires to do it. So this is one of the things that makes quantum computing really kind of neat. The Fourier transform happens to have this beautiful structure that maps itself kind of amazingly well onto a quantum computer, which is this tensor product structure. And by exploiting the tensor product structure, we can do an analogous transformation using exponentially fewer operations than the classical one. And again, this is fantastic because the Fourier transform is very, very useful for transforming information from phase into bits. So next lecture, we're going to see how we can do this and show that we can do phase estimation by doing a transformation that ends up looking like QFT acting on a bunch of 0 bits coming in like this, and then having a sequence of controlled unitary operations going down over here through to u to the 2 to the n on that side. UFT inverse. And then we'll see that the quantum state that we end up getting out after doing this is going to be a eigenphase of u, where the eigenphase is all the eigenvectors or eigenvalues of u are of the form e to the I theta j, where these we call eigenphase. So these eigenphases that represent the eigenvalues are actually just going to be directly output as bit strings on that top register, within actually some error, depending on whether or not the eigenvalue or eigenphases happen to divide 2 pi. So the next time we're going to be going through the analysis showing that the quantum Fourier transform, in fact, is capable of doing phase estimation, and also we're going to be going through the work in order to show how you can do addition using quantum Fourier transforms. This was bedrock behind a Draper adder, which is also used as internal subroutine inside Shor's algorithm. So again, thank you very much. If anybody has any questions, please don't hesitate to bug me about this. Take care and see you next time.